All right, so welcome everybody. I'd like to let folks know, I see a few new faces, of course, that we are operating here under two different codes of conduct. Microsoft is nice enough to let us use their facility free of charge. And so we're operating under the Microsoft Code of Conduct, as you can see. And we're also operating under the Rust Code of Conduct. In a nutshell, it asks you to treat others with dignity and respect. And if you find that somebody is not treating you that way, or if you feel that somebody is not treating you that way, please let them know. If the behavior does not stop, please let me know, and I would take it from there. Let's see, we have a Discord. So if you would like to interact with us, particularly as things go on, please take a screenshot of our Discord invite link, and you can join us on the Discord channel and ask about more information, or who was that person who did this presentation, blah, 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 and we can connect you up with whatever you might need to know. These slides, as always, are available at slides.com under U007D. That's my online alias. So you'll be able to find this slide deck as well as all the previous months at that URL. We like to do introductions, so here we go. My name's Brad. As I just said, my online handle is, I started tech way back when the dinosaurs were roaming the earth. And I have a BSc in computer science, started in BASIC on a Commodore 64. Quickly realized that the version of BASIC that was included on that computer didn't get you very far. And you quickly had to get into peeks and pokes, which is basically pointer dereferencing. We would know that as today. And then ultimately you'd be into assembly language, PDQ with that machine. And I think that was a fantastic introduction to technology because you really got to see how things work while they were simple. And that's actually sort of the underlying driving force behind why I'm running the embedded series with this group. Because I'd like, with computers like this today, with 128 gigs of RAM, what the heck's going on in there? Who can tell, right? But if we can get back to really, really simple computers, $6 computers, they're still dual proc. They still have two processors in them. But if we can get back to really simple computers, folks can learn really how computers work. And all those principles scale up to all the other computers you're ever going to touch. And I think Rust is a great language to interact with all of that in. So that's why we do it. And hopefully that intrigues you and makes you want to give it a shot. Do we have Adi? Are you here tonight? Checking faces real quick. Nope, guess not. So Adi is our basically he's our person who's helping us line up all the speakers. And so you'll see him as Zorro with one R on Discord in our Discord server. And so he's the person putting all of the speaker lineup together. I was going to have him introduce himself, but we'll have to save that for another night. And because we don't get to meet each other very much, if I'm busy lecturing, talking to you, I would like to open up the floor. Anybody want to introduce themselves to the group? Tell us a little bit about yourself, maybe why you're here, what your background is, or what your interests are. Nice. That's cool. Welcome. All right. Anyone else?
It's my first time coming to this, but I've been tech reading for like 8 years now. Somehow just never found my way here.
Well, welcome as well. So I might use the mic just so that the people can hear on the recording. I'm new to this, I forgot. All right. Would anyone else like to say hello? Yep, okay.
My name is Matt. I'm an optical scientist, and I'm learning Rust to hopefully work on some projects.
Very nice. And right behind you as well.
I'm Chris. I maintain the zip crate for Rust, and I'm also a software engineer at Amazon.
Nice to meet you both. All right. Anyone else like to say hello? Yeah. Yep. All right. We'll do it. That's right. No worries. It's all good. It's all good.
Oh, there we go. Great. Hey, everybody. My name's Sean. I've been interested in Rust pre 1.0, just saw tons of potential in that. So I spent a lot of time writing a bunch of little libraries in the corners on GitHub. And I use Rust, my job at Google, writing WLAN for Fuchsia.
Writing W.
WLAN. I work on Wi-Fi on the Fuchsia operating
Oh,
system,
wow.
yeah, which most of that stack is written in Rust.
Very cool. All right. Yep.
Hey, my name's Wes, and I guess I got interested in Rust maybe about a year ago. Haven't really done too much with it, but I've mostly been a Python guy, and did C in school, and I guess I was interested in a language that wasn't gonna segfault me, so that sounded pretty cool. But I'm an SRE at TikTok right now for live streaming.
Very cool. All right. We've got time for one more in the back. Yeah, the green shirt.
Howdy, my name's Pete, and I used to work on the Chrome browser, and I wanted to learn Rust to write memory-safe code, but now that I don't, it's sort of like learning it after the horse has left, shutting the barn door. But I still am very interested in learning to write in memory-safe ways. And Brad, I want to thank you because I've been asking questions on the Discord about what ohm resistors do I use for this project. So thanks for all those answers.
Oh, you're welcome. You're welcome. It's nice to put a face to a handle. All right, that's wonderful. Yeah, a lot of information will flow from the speaker to the audience, but it's really important that everybody feels that this is their group and people get a chance to talk, share interests, particularly as we, well, I'll do this slightly out of order. As we often do social events, we can, in the summertime when the weather's nice, we try to leave on time so that way our hosts can actually get home and have their dinner and so on. So often we'll congregate just outside the door and there's a big crowd of people and the conversation can go on for over an hour. But as the weather sort of goes south, we also would gather at the Flat Stick Pub over at Redmond Town Center, not too far away. So if folks are interested in that, that's what we'll do after the meeting. If you're new to the area and you don't know where Redmond Town Center is, or you don't know what Flat Stick Pub is, let me know or see anyone else here and we'll give you the directions on how to get there. It's not far. Upcoming meetups, August 15th. We have been alternating between this lecture format that we're going to do tonight, as well as the embedded systems hands-on, where everybody brings their computers and they use these little Raspberry Pi Pico kits, and we actually do bare metal Rust embedded programming live here. We've been alternating each month. This or next month would be the time where we do another embedded system. But I think what I want to do for next month is do a session dedicated to the beginners. So for those who are new to this group, about 60% of the group identifies themselves as beginners in Rust. So you may be looking at a lot of faces thinking, I'm the only one who doesn't understand, the intricacies of Rust, but actually the majority of us are saying that's who we are. So I wanted to create some more content for the beginners. So that's what August will be dedicated to. If that's not your cup of tea, that's okay. If we have any luck, you'll be able to stream this at home live. So we can try that experiment. No guarantees though. So, you better show up here if you want to know it for sure or want to see it for sure. Then we'll do September 19th and October 17th. We usually meet the third Thursday of every month, unless there's a scheduling conflict with the reactor. All right, any questions about anything so far?
Do we always meet here or do we ever meet closer to Seattle?
We always meet here. So that's one of the reasons why I think some folks are asking if there's going to be an online or live stream component. I know it's a lot of work for the Seattle folks to get out here. We did a lot of research at the beginning, hitting up Seattle Public Library, we hit up UW, we hit up a number of different places looking for venues. And this is the one venue that responded and said, "Yeah, we can do this."
Did you ask Amazon?
We did not. Yeah, it's going to be 6 of one, half a dozen of another. But as we get ourselves more digitally present, then I think it's going to ease. Like if it's just too much traffic and you don't have time tonight, you can tune in online. And if it's a live stream, it should be able, you should be able to interact as well. They tell me it works, so fingers crossed. All right, so one of the things I want to do is sort of pick up a little bit of Rust community news for the group that you may or may not have heard of. What I would say today, or for this month, is I picked a sort of a series of events that have been going on recently that I think are interesting. If anything, this is sort of the not Rust community news, right? This is the community news that Rust is helping to shape. It's quite interesting. So the U.S. government is saying things like last December, the U.S. government put out a recommendation for organizations to use memory-safe languages. And it's for cybersecurity, national security, the FBI, all the 3-letter acronym organizations are all behind this, saying, for our own sakes, we ought to be using memory-safe languages. And so if we get into this document, it goes through and it lists a whole bunch of languages that qualify. And there's C# and there's Go and there's a whole bunch of languages. But there's exactly one language on that list that's not garbage collected. And we all know what that is. So what's interesting about this, yeah, exactly, it's Ada, right? What's interesting about this is there are applications that a garbage collected language is not suitable for. And the $6 Raspberry Pis with 264 kilobytes of memory on them would be an example. So it is not that expensive for us today to build a multi-megabyte embedded systems device. But a 264 kilobyte embedded systems device is always going to be cheaper. And so what's interesting is that there are still applications where very efficient languages that are not garbage collected, there's always going to be a use case for them. And what's interesting is Rust is the only one that made this list. C++, famously all about performance, there's an article that's come out recently. C++ is taking notice. And what's interesting about the C++ community is that they are also looking at ways in which to make C++ safer. I think I used to work in C++ before, switching over to Rust in 2014, 2015. So I spent many, many years there. I think they have their work cut out for them, right, to sort of make that work. But I'm 100% behind the initiative, 100% behind this, because we are going to be living for the next century or more with a C++ code base, right? Even if all the code that was being written in C or C++ switched over to Rust tomorrow, which we know that's not going to happen. Even if we switched over tomorrow, we're going to be living with billions, if not trillions of lines of C++ code for a century. It's in our cars, it's in our airplanes, it's in our elevators, right? It needs to be safer. So I'm 100% behind this initiative. What I see is that C++ is breaking down, at least at the moment, in their efforts to get more safety into 4 different directions. One is stick with C++ as a standard and apply C++, something called C++ core guidelines. It's like this, use only the safer parts of the language. It's like C++, the good parts, right? Now, the core guidelines is a 350-page document that you have to kind of know and use, but with enough experience, it's possible. And there are 3 C++ forks, if you will, of the language that have come out, called Circle, Carbon, and CPP Front. They have very interesting and somewhat unique takes on how to approach safety with C++. So if this stuff is of interest to you in any way, definitely pick up the slide deck and take a look at some of this stuff, because this is what's going on around us, and largely as a result of what Rust has done and the success that Rust is now enjoying. So I think that's worthwhile. So what's next? What I think is next, if I were a betting man, I think one of the next revolutionary languages is going to be Mojo. So it is also a memory safe language. It's written by Chris Latner, who wrote LLVM, who's the lead for the LLVM team. And he's using some technology that none of the other languages are using, including Rust, to make code that's much, much faster. So it's something that you might want to pay close attention to if you're interested in, I don't know, high performance computing or anything like that. And there's also another language, I don't know how to pronounce it, Hilo or Hilo. Formerly it was called Val, but they're using a technique called mutable value semantics. There's a bunch of white papers out there that you can link to through this link. And it explains how they do borrow checker without the complexity. So what their claim to fame is, they claim to be just as safe as Rust because they're employing technology that does the same thing that the borrow checker does, except you don't have to worry about it as a programmer. It just works. That's kind of cool. Like if it's true, right? That's kind of cool. So they've got a white paper out and they've circulated it. It's been out for more than a year. The white paper's been out for more than a year, and it seems to have been holding up to peer review so far. So that's kind of interesting. So I just wanted to sort of bring that out to say, like, there's a lot of change going on in the industry right now, and a lot of it's being driven by, this language that we know, love, or are learning how to use, and keep your eyes peeled for other great movements in safe languages, because it's more than just one language. Any thoughts, questions, comments? What happened to Ada? No, they didn't. That's the simple answer. What do you think happened to Ada? Yeah.
Somewhere along the way, they had two where it's like,
Right.
we got to be there. Back to
Yeah.
also for Latner, the Objective C rebuild of final Swift.
Yep.
With most
Yep.
they actually did that. Well, yeah, let's try a new language because one that we built the company. Well, get rid of it.
Yeah, not just any company, right? So what Chris Latner did to convince Apple to switch to Swift is nothing short of incredible, right? Oh yeah.
Didn't actually have to convince the whole company. They only had to convince the secret project that they were switching, and for the rest of it, like, hey, guess what? Swift.
Once you get the Illuminati, everybody else just followed along. That's very smart. That's very smart. Yeah, well, send the link to that video out in the interview if you to the Discord if you have it. That would be very interesting, I think. Yeah, thank you guys. That's great. That's great. Anyway, so I'll just try to pick something, each month, and if there's something that you think would be cool to talk about here that you're interested in, let me know, and your line will be on this slide, and you can come up and talk to this slide. But yeah, just take 5 or 8 minutes and share something that you think is interesting that's going on out there.
Quick question. Did you read the ICA recommendation paper?
I've not read the whole paper, no. No.
Just curious if they're trying to address, like you said, airplanes, elevators, all that.
Yeah.
And the safety going forward is good. The new code will be safer, but
Yes.
there needs to be a way to make the previous things that will keep running for centuries secure. And I
Right.
don't know if there's that's why I'm so skeptical. If it's okay, Warehouse said something, but it's not gonna actually make people rewrite these things. They're gonna keep being there, being unsecure. Yeah.
Yes and no. What's been really interesting is since December 23rd, 2023, when that paper came out, Microsoft came out and said 70% of the most serious bugs that we've encountered over the past 20 years are not possible to reproduce in Rust. Google came out and said the same thing. AWS came out and said the same thing, right? There's also a number of players that came out all within 6 months, right? And I think it's all part of this effort. It's a coordinated, these people are talking and working together. And I would say spring of 2024 versus spring of 2023 was very different. Is the US government saying use memory safe languages going to erase all of our technology problems? Of course, absolutely not. But what it does is it's making everybody think very, very seriously about this. There's some folks in here from Blue Origin, there's folks here from SpaceX, and even they'll tell you that Rust is making inroads into aerospace. It's maybe now in the ground service equipment, but it's moving to other places. There's a person in the room who has some Rust in space right now. So it's making these inroads, and a lot of it has to do with the fact that it's not because it's a safe language, it's because it's a safe bet. As a decision maker at a company, I don't want to take a lot of political risk. But when I have the air cover of the US government behind me and Microsoft and these guys, I can point to these papers and say, you know what, maybe we should take a look at this. And that's where I think it's making the difference. We still have to do the hard work of chipping away at that legacy code base and making it safer. I'm not suggesting we should port it all to Rust. I'm suggesting we should make it safer, right? However we need to do it. But I think providing the impetus to do that and the credibility to do that, taking memory safety seriously is important. C++, I would say, is guilty of caring about speed more than safety. And this is a reality check to that. I think it's long overdue. All right. Okay, so we've got 2 talks tonight. One of these is one of the talks we're going to have. The other one is a lie. Rust can compete with Python by Jack. Jack will be doing that talk first, and then we'll be followed by another talk. Unfortunately, Dylan is unavailable tonight, so he won't be able to do the performance, Rust for performance on the Beam. So we'll have to schedule that for another meeting, and I'll be doing a talk with you guys. And we'll talk about what that talk will be right now. So I talked about we're going to do some beginner talks starting in August. I think I'll try to pull one of those forward. I have one in mind, but I would like to ask the beginners in the room, what would you like to hear about? And for those in the room who are not beginners, I would like to ask you, what is it you're hearing over and over and over again from beginners that you think might be useful for us to talk about? So that gives everybody in the room something to think about and to suggest. Dependency management. Could I ask someone to capture this? Thank you, Adi. So we had dependency management. What was this? Private and private registries. Okay. Beginner topic, private registries. Okay. Okay. That's a great topic. Yes. Do you really have to understand Box, Arc, and RC? Or can you just clone your way through? For beginners, you think?
No, for things you can skate through, not really understand.
Oh, yeah. Or async.
Like we could call them carpets. Beginners get stuck in that maybe they.
Yeah, what's interesting about the Box and Arc and RC is there's a solution to that, right? You can't clone your way out of async though. Yeah. Await your way out of it. I love it. Mm. Yep. Yep. Okay, that's great. And error handling would be another one for beginners. I did a live coding example of that was over 2 nights when we rebooted this group July. I guess it'd be a year ago now. But now that we're recording, maybe it would be a good time to redo that. We also have lots of new faces in the room since then. Be a good time to redo that. And then there's there will be a record of it that we can point folks to as a resource. So that's a great thought. Yep. Mm-hmm. Yeah. Tour of unsafe. Yeah, yeah. That's really interesting. Unsafe for beginners is an interesting topic because unsafe is more difficult in Rust than using an unsafe language. Right? That sounds weird, but like if you said, I'm a beginner, should I use I'm a beginner in CS. I don't know either language. But should I use unsafe in Rust or should I use C or C++? I would
On that level, beginners will not have that question.
I would say probably not, but I would say you're going to have a much easier. I've never, yeah, I'm it's very timely you bring this up. Had you told me this a week ago or 2 weeks ago, I would have said I've never had to use unsafe. Really? I mean, I do embedded systems, so there's a tiny bit. That's fairly straight. No, it's just like to deref to access the contents of a raw pointer, you can use unsafe right around that deref, and there's not much to know. But when you start using unsafe in a more general way, things get hairy in a hurry. So I would argue that is not a beginner topic. But what's interesting about that is just telling beginners don't do it isn't a very good answer. So to have a talk maybe about why and to give a beginner level understanding of what's dangerous about it, I think would be a really interesting talk. So thank you for that suggestion. Yeah, why is unsafe unsafe? Why is unsafe not suitable for beginners to touch? Like those are really good questions.
To come languages like C and C++, they can do the same thing as they do in C++ in Rust.
Right.
And so there's some lack of beginner resources, people coming from those languages.
Yeah,
that
yeah.
Want to do something with memory.
Yeah. Yeah, this is my whole week this week. Yeah. Yeah, just simply like give me a block of memory and I want to treat it as a foo. No. Mm-mm. I wish it was that simple. Did you catch that one, Adi? The unsafe for beginners? Okay, and I saw the hand over here. Yes. Right. Okay.
Level perspective. Intro to CI/CD, S-bombs.
Very cool. All right. So the request was for Rust toolchain, maybe cargo in particular, and then maybe as an intermediate talk, CI/CD and hermetically sealed tool chains, deterministic builds, those types of things. Okay. Yes. Lifetimes for dummies. Yes, that's a huge pain point for beginners. It's like, what are all this? One quote. I don't understand. Yeah. So lifetime for beginners. Yes. Yeah. So,
Trades,
yeah.
generics and all this. the types and how you do all that stuff.
Inheritance and polymorphism. How to do it in Rust. Sorry? I would say specific. I mean, I guess I could go a lot of directions with that, or we could go a lot of directions with that, but I think specifically sort of repeating some patterns you're familiar with in Rust does, you know, it doesn't work so well. Yes. Bite muck, the crate?
Yeah, in fact, a lot of beginners could probably benefit from knowing how to use BiteMuck before they know how to use unsafe.
What problem would this be solving? What problem do you envision this solving for the beginner?
Well, mostly type conversion of structs when performance is a concern.
I see, I see.
Because, for instance, in the zip crate, we have to deal with a lot of headers that have fields that are only 2 or 4 bytes long. And
Right.
we're currently using unsafe to serialize and deserialize those in larger units.
Yeah, yeah. Probably thinking more intermediate level, but I think that could be interesting. Do you want to put bite muck down, Adi, for intermediate level conversation? But it's the name of a crate. All right, those. Oh, go, Carl. Yeah, they see it, and so you're gonna be like, "What's that?" And you can't be like, "Don't worry about it." Like I'm about to tell you guys to not worry about it. Like, no. Yeah. Okay.
Yeah,
All right.
it comes up when you're doing error handling,
Definitely. Yeah.
and that threw me this week.
Or when you're trying to build a graph of different types of tasks.
Right. Any heterogeneous container. There's lots of reasons it'll come up. So let's just say a trait object as well, please, Adi, or Dyn, maybe DYN, and Jack. We'll wrap up with you. Right. Yeah, I think I think that unsafe talk for beginners is going to be a really good talk. I wonder who's going to give it. Looking for volunteers. All right, that's great. Thank you. All right, so let's keep moving here. Those are some fantastic ideas. And what I'm thinking about doing is whether we mix in one beginner talk with whatever other talks we have each month. So that way there's something each month for beginners and non-beginners. Or, whether we, have some way of dedicating a meetup to, say, beginner topics. We'll get that figured out. But I just want there to be a continual cadence of really good introductory content for folks. Mm-hmm. Mm-hmm. Okay. Okay. So that last one, Adi, was the use of option and the lack of null is weird for people who've not seen that before. Monads. All right. That's great. Thank you. All right, so let's switch over. We're gonna, because for the purposes of time, we're gonna jump into a presentation with Jack. It's gonna take us a couple minutes to plug in. Do you need to plug in your computer? Oh, sure thing.
Your little 2 blue arrows in the bottom right. I know Reveal.js when I see it. Got some Reveal.js.
I will.
Coming your way.
I will leave you to it. Do you want to use this, or would you like to use the lapel mic? The other one is live. Okay. Now you're on.
Okay, so am I audible in the room? I have sworn that I will keep this to 45 minutes, so I'm going to put a little stopwatch on for myself. Okay, and then do I know how to full screen things in Mac OS? Is that the green button? It wasn't. Is it F11?
No, it's not.
Okay.
It's
That's right.
is this
It's full screen, but not full screen. You know what I mean?
Yeah, I don't know how to do.
I'm about to try F11.
You thought I would.
View does seem.
It says exit full screen. It thinks it's in full screen.
I'm going to press F11, and if that doesn't work, I'm going to give up. It didn't. All right, well, here we are. Oh, definitely need to mute myself and kill that. It did? Yeah, I did that. All right, we get title bars. That's fine. Cool. So I'm going to talk about how we compare Rust and Python. I'm going to try to thread the needle a little bit. Like Brad said, there's a bunch of people here who are, if not complete beginners, maybe folks who still feel like beginners sometimes. There's a lot of folks here who are very experienced. I'm curious, raise your hand if you're like comfortable in Rust, whatever that means to you. It's like half the room, right? Raise your hand if you're comfortable in Python. Unsurprising that there's almost as many people comfortable with Python as comfortable with Rust at a Rust meetup, because Python is very popular. Yeah, I'm intending this talk to be kind of an introduction, but I have a lot of slides and I'm going to go fast and I'm going to cheat. So it's going to be a bad introduction and I apologize in advance. But I also want to tell a story, and hopefully that story will be at least mildly interesting to those of us who know all these topics. I want to talk in part about why I think Rust is as hyped as it is, why the hype train has been going so hard for 7 or 8 years. So we're going to talk about Rust and Python and kind of tell that story. And that's going to be a way for me to talk about some features of Rust that I usually don't get to talk about when I introduce Rust. And maybe those of you who've taught other people, maybe you do what I do, which is usually when we're introducing Rust, we're telling this story, right? We're comparing Rust to C and C++. And of course, Brad opened this entire meetup with a good chunk of interesting news about this story. So of course, this is the story we usually tell, right? This is a very exciting story. C and C++ had like no competition for 30 years or something like that, right? In the sort of native language space. If you were programming a toaster or winning the benchmarks competition or whatever, like you had 2 choices, right? So of course, it's very exciting that Rust comes along. You got these other options. That is certainly like the biggest reason Rust is as hyped as it is. And I think we all understand that. A lot of us have heard this story. A lot of us have told this story, right? It's not the story I want to tell today. Today, I want to talk about how Rust compares to these languages, right? Raise your hand if you know one of these. Everyone, right? Or just about everybody has at least touched something like this in school, at work, whatever. These are the managed languages, the garbage collected languages. And I think, when we don't need to be, I need to be standing in front of that? Oh,
That's your camera.
hello. Hey, everybody in the world. So when we don't need to be like programming toasters or whatever, right? We don't need to be winning the benchmarks game. We usually pick one of these, right? We don't usually use C or C++ unless we have to use C and C++. That was a story for a long time, right? And I think, we've all heard or understood or encountered ourselves like the reasons for that, right? C and C++ make some trade-offs, like a little harder to learn. There's these new bugs you have to worry about, the memory safety bugs. And what you're getting for that, if you use C and C++, is usually speed, or maybe like the toaster thing, And so if you don't need those things, then C and C++ don't help you get your work done. And that's why these languages are so popular, right? These languages are mostly about getting your work done. But these languages do make a lot of trade-offs, right? I think the most familiar trade-off, again, probably everyone in this room has at least played with a dynamically typed language and a statically typed language. I think most of us know what that means. And that's a common trade-off in this space, right? So statically typed languages like Java, Go, right? A little bit harder to learn, a little bit harder to write, but they're catching all these bugs for you, right? That's a normal trade-off within this group, right? And those languages, even if they're a little harder to write, are helping us get our work done. So we make trade-offs like that all the time. And the story I want to tell is how I think Rust can sort of sit at the same table, Rust can offer you the same trade-offs as those dynamic languages, as those managed or garbage collected languages. And if all you need is to get your work done, and you don't care about programming toasters and winning benchmark competitions, and you don't need speed, you just want to get your work done, but you're willing to pay, a learning tax, right? Rust certainly is harder to learn than anything that was on that previous slide. But if you're willing to pay a learning tax, Rust can offer you the chance to catch whole categories of bugs that other languages up until now have not usually caught for us. It's sort of like choosing static typing, like choosing like static typing on steroids or something like that. It's big learning tax, right? Sometimes it's a coding tax too, but we're catching enormous categories of bugs. So that's the story we're going to be telling today. That's what we're going to talk about. We're going to talk about enums and how they help us catch null pointer bugs. We're going to talk about destructors, how they help us catch resource leaks. And we're going to talk about aliasing rules and how they catch what we sometimes call spooky action at a distance because we like confusing metaphors. All right, so I'm going to launch right into it. We're going to talk about enums. For the purposes of this talk, I really wish I had that full screen. Well, bear with me. Oh, that's a good point. That's good. OK. This is solarized light, sir. So this is an example of some Python code. Don't read it. It's like too much code to read on one slide. I'm going to zoom in on it. But I'm going to use Python as my foil for this talk, right? That's the title of the talk. It wasn't a lie. But I want you all to feel free to imagine that this was Ruby. I heard someone say they read a lot of Ruby. Imagine that this was Java. Imagine that this was Go. Whatever you're familiar with and comfortable with, because almost everything I'm going to be saying and comparing Rust to applies to the entire category of managed languages. In the respects we're talking about today, you could swap out whatever you like. So imagine you could sort of mentally translate. Hopefully Python, even if you don't write a lot of it, is relatively easy to read. That's one of the things it's famous for. Feel free to translate as we go. So here's an example program. And I'm introducing this program just so that we can talk about null pointers, right? We can talk about none in Python. That's Python's null. So what does this program do? It screams hello world. Oh, no, I don't want the definition of that. And it has one feature, right? It can scream hello world into a file, right? You go to file path on the command line, it can do that. So there's like some modes, right? Let's look at the code finally. We've got a class. It has a constructor. The constructor has a path argument. That path argument is optional. This is how we write that in Python, right? So none is like Python's null, like Golang's nil, right? We probably have all seen some language that has something that starts with an N. If we have the file, we open it. If we have the path, we open it. We get a file. Otherwise, we don't. There's a write method. There's the screaming, right there. We might have the file. We might not have the file. Depending on what mode we're in, we do different things, right? And this is where we construct it. sys.argv, right? That's the arguments vector. That's our command line arguments. We open the thing in one of two different ways, and we run it. So nothing too crazy here, but this is a chance to talk about none and null in general, right? A lot of familiar bugs, right? This is, I think it was Tony Hoare who called null pointers the $1 billion mistake. I think most of us have heard that story, right? And we've all ran into these bugs. We probably all ran into these bugs in our first programming class ever. This is null pointer bugs. And you find out about this when you run the code, right? These are runtime bugs, sometimes a little hard to catch. Sometimes we have to write a lot of tests. We could forget to check whether path was none. If we open it, we crash. We could forget to check whether we have the file or not in the right method. And if we forget to check, sometimes we crash, right? Null pointer bugs. Super familiar, I think, to everybody. So let's see what Rust does. Rust, for this kind of code, this is, again, it's too much code to read. Don't read it. It's too much code to read. But for this kind of code, Rust is not going to use null pointers. Rust is going to use what we call enums. And again, I'm going to go a little quickly through here because I know for a lot of people this is all very familiar anyway. But let's take a quick look at how we use enums in the same situation. Cargo, the Rust build system, right? The way we run a Rust program generally. Same feature, right? Take command line argument. Let's look at it. So screaming output is an enum. And for those of you who have not seen this yet, and I know there are some of you in the audience, this is a little different, right, from the C or Java or even Python enums, right? Python has import enum, and all of those things are usually fancy ways to give names to numbers, right? Those are like named integer values. This is sort of that. It can be that, but the huge difference is we have data, right? So our screaming output enum can be a file, or it can be standard output. It has these two different modes, and in the file mode, and only in the file mode, it's got a field, right? So that's what makes enums so different in Rust. Rust is not the only language that does this. I think Kotlin has something similar. Swift has something similar. I think Swift even calls it enum. But Rust is, most of the languages on the previous slide, the common popular managed languages don't do enums quite like this. And the way we use this is we match on it. We have the match keyword. So here's the right method. I've zoomed into it. And there's the screaming, just like Python, fine. And we match on self. And when we match on self, self was that screaming output enum, right? And we have to say, OK, in this case, do this. In this case, do that. And in the file case, we name the file member and we have it in scope, right? So we can use file here, and we don't have file here. Again, I know this is familiar to a lot of people, but I wanted to highlight it because I know some people have not seen it yet. And one last example, this is going to be, if this is your first time seeing some of these, probably way too fast. But I like to point out, it's very normal to see like 2 or 3 different kinds of enums in the same function. So here's the new function for my screaming output. And I have an optional path, right? So the path cannot be null. There's no null in safe Rust. We use option, and it turns out that option is also an enum. I think some folks might even have mentioned earlier that they like talking about option or want to hear more about option. Unfortunately, I have too many slides to really like zoom in on it. But we're matching on the option. Now, option is not our custom enum, right? Screaming output, that's ours. We wrote that. Option is a standard Rust enum. It's in the prelude or the global scope. We match on it, and it's got these 2 states it can be in. And in one of these states, it has data. And the difference between parentheses and curly braces doesn't matter. And this is the same idea. So path is in scope here, but not here. So we have to check this when we use it. And of course, result, those of us who've seen error handling in Rust before, know that result is also an enum. And this question mark operator that we use for handling results, for returning the errors if we see them, is syntactic sugar. It's a little shortcut for a match, right? So enums are everywhere in Rust, absolutely everywhere. We use them constantly. This is a perfectly normal tiny little function, and there's 3 different types of enums in it. We use custom ones, and we use standard ones. OK, so we can make the same mistakes as we made in Python. And those of us who've done this in Rust know that the big difference here is that these are now build time mistakes, right? Anyone who's used a compiled language has seen build time mistakes, and they are very frustrating when we learn our compiled languages because they mean we can't run our code and get our homework done. But once we get our, once we start getting into the, rhythm of doing our work, these are very nice because these errors are guaranteed to show up, right? If we forget to check the path for none, it's a compile time error. If we forget to check the file, there is no self.file, right? The only way to get at the file is to match self, right? That's how enums work in Rust. These are compile time errors. My favorite thing about enums is kind of how they help us maintain our programs as they grow. So this little example diff is me adding some stuff, right? I've added the path field here in the file mode. Maybe I want to log it or something, right? Something. I've added the standard error variant. So now instead of 2 modes, I have 3 modes, right? Maybe I could print standard error. And as soon as I do this, Rust is going to go boom, 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 boom. And I'm going to have this nice list of compiler errors coming out at me. And they're not angry errors. They're happy little errors because they're helping me, right? They're saying, hey, you good for you. You've added these features. That's so great. Now go ahead and update all the places in your code where you use this enum, right? This is great. It is very nice when this happens, right? Because, hey, last time we created a file, we created it with just that one file field. Now we said there's a path field. Rust is going to remind us to put the path field there. Last time we matched on self, this was inside the right method. There were 2 modes, right? We had file and standard out, and now there's a 3rd mode. We'd better go say what happens in that 3rd mode, right? So by default, you can opt out of this, but by default, Rust is going to force you to actually say what to do with all the variants of the enums that you have. And this is very, very helpful. My favorite way to think about, just the highfalutin way to think about what this is doing to our code, is it's helping us say exactly what states we expect our program to be in, or what states we expect this object to be in, right? So this object has 3 states, right? Now it has 3 because I added the 3rd one, right? It can be a file, it can be standard out, it can be standard error, 3 states, right? It's easy to read. But imagine how many states it could be in if we were writing this in Python or in anything, right? Or even if we were just writing it in Rust, but we were using like option separately for the file and separately for the path, and maybe standard error was a Boolean flag or something, right? In whatever language, of course you can do this, but if the file is like optional nullable and the path is optional nullable, and you've got some other Boolean flag for standard error, well, that's 2 times 2 times 2 is 8 different states that your object can be in. And you probably did not want 5 of them, right? So being able to tell the language, like, hey, like take that state space and squash it down for me, please, because these are the states that I consider meaningful and valid. Very helpful. And the tools help you out when you help the tools. So that's what enums are all about. Again, Rust is not the only language that does this. The functional languages, if anybody knows of functional programming languages, we're also very famous for doing this. I think Dylan was going to give a talk about functional languages, and I'm very sad that we're not going to get that today. Hopefully we get it later. I will bring functional languages back up again at the end. But that's enums. Let's talk about destructors. So destructors, of course, is the C++ term for what we're about to talk about, right? This is the cleanup function that runs when things go out of scope, and Rust calls that drop. And we're not going to look at how we do it custom ourselves. We're just going to look at how the object we were already using get cleaned up. And in this section, I want to ask a question. This section is about asking a question. Here's the main function from that last Rust program we were just looking at. I don't think we scrolled down to main, but there it is. Not much to see. And my question is, do we have to worry about closing any of these files? Like, we've just been writing a bunch of code that opens files, and we probably sometimes want to close them. Is that a problem? Like, what's going on here? And Rust's answer to that is very straightforward. It's like, no, you don't have to worry about that. This file is going to get closed automatically. So the rule in Rust is I called this local variable output when I open the screaming output, and that's going to go out of scope here at the close curly brace. And Rust is going to drop it, and that means clean it up. And when we drop things in Rust, if those things have fields, we drop their fields. So Rust is just going to automatically look in there and ask, oh, is this a file? Because if it's a file, I'm going to drop that file, the standard FS file on the inside. And we can go read the docs for standard FS file, and we can see that it says that when you drop it, it closes itself. And that's great, right? And files closing themselves are sort of like the textbook thing that destructors are for, right? That's why we like them. They're convenient. I want to do a quick science experiment, because we might be like, are we sure this thing is like actually getting closed? And I want to get sure, because doing this little science experiment will help us talk about Python after. So here's a tiny little Rust program that helps us get sure that the file is being closed, right? So what am I doing? I don't know. I'm printing like some numbers or something. So this function that I've written is called look at file descriptors. And I'm sure only about half the room has heard this term before. So like when we open a file, what are we actually doing? We're asking the operating system to open it for us. And what does the operating system do? I don't know, some stuff. But then the operating system like hands back some sort of number, some handle to refer to the open file. Right? We call this a file descriptor. And we normally don't have to think about this at all. But under the covers, this is how everything's working. And if we go ahead and print the file descriptors, here I'm calling this function 3 times, which is why we have 3 lines. If we print them, we can see them. They're kind of like pointers, but we see that the numbers are much smaller. And OK, so we open dev null twice, and we print the file descriptors, and we repeat that a bunch of times. And we're seeing 34, 34, 34 each time. And we can know, this is not obvious if it's your first time looking at this, but this is telling us that those files are getting closed. Because if they weren't getting closed, we would not see 34, 34, 34. We would see 3, 4, 5, 6, 7, 8. Right? So if a file is still open, or a handle to a file is still open, then the operating system cannot reuse that number for another file handle. It needs to use a different number so that they all refer to different file handles. But it's reusing the numbers, and the reason it is doing that is because we close those files. Cool. That's what the doc said was going to happen, so that's cool. There's other ways we could do it. We could run strace or other fancy stuff. We're not going to do any of that. So now my question is, what happens in Python? Do we need to close the file in Python? Does the file get closed automatically? Should I quiz the room? Answers, right? Shout out answers. With. I'm going to make it so that we can't use with. That was an excellent suggestion. I'm going to conspire to make that not work for us. The answer is complicated. The answer is, so here's my science experiment, but in Python. And you can see some numbers on the right side, and those numbers are not all the same as each other, are they? It turns out there's more than one Python. And so this is, if you use Python on the command line or Python 3, this is it. This is 99% of the time, that's what you're using. C Python on GitHub or whatever, right? There, OK, we see the files are closed. That's cool. I know some people in the audience know what reference counting is. Good for you, right? So C Python is somehow managing to close these files quickly, but there are other Pythons. PyPy is like another one. It's like faster sometimes. Some companies like to use it for that reason. It's not like super common, but some people run their code under PyPy. MicroPython, if you run code on these Raspberry Pi Picos that we've been playing with, if you run Python code on those, which you can do, I think, that's MicroPython, right, running on your toaster. So there are just a lot of Pythons, and the Python standard doesn't necessarily say exactly how they're supposed to clean up objects, and some of them do that reference counting thing that some of us know what it means, and others don't. And if they don't, and most of the managed languages on that slide, right, Java, Go, right, the usual suspects, most of them do what these bottom two do, sort of mark and sweep garbage collection or some other buzzword, right? Something, 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 they do the work later. They don't necessarily do the work now. And here's a final piece of trivia, final science experiment. It turns out we can make CPython, the standard Python, clean these files up later. I'll do this like back forth thing so that you can see the numbers change. Just look at the numbers on the right, right? They changed, right? And if you know what a reference cycle is, awesome. Feel free to read this code and like think about like, oh yeah, that's a reference cycle. If you've never heard of that, it doesn't matter because we're deep in the trivia. But you can just remember the only important thing to remember, which is that Python does not guarantee that it's going to close your files quickly, just like Java doesn't, just like Go doesn't. And so any experienced programmer in any of these languages will tell you that you need to do it. You need to use something like the with keyword that he just mentioned, right? Or whatever strategy to close files. It is not great to just leave them sitting around because the number of files we're allowed to have open is not that big, right? It's like 1,000 or whatever by default on my machine. It's configurable, everyone's different, but like it's not that big. And if you leak them over time in a longer running program, you will eventually regret it. So we should close the file, right? We should probably do something. This is the bare minimum approach. Again, some of the more experienced programmers in the room probably instantly spot the fact that I have not handled errors in this example. So if the write function throws an exception, then we're never going to get to close. And in this case, this is like a short-lived script and no one cares, right? Because everything's going to get cleaned up when it exits. But you could imagine that this code was in a longer running program and we might care, about leaking files even in error cases. So we can write try finally. This is the familiar, come from Java, come from C++, right? I think everybody's probably seen those keywords in some flavor. So this is the first example that is actually correct in both the happy path and the error case for cleaning up this file. I'm not going to use the with keyword quite yet. We could wire up screaming output to use the with keyword. More experienced Python programmers know what that is. Instead, I'm going to make this example just a little bit more complicated to make the resource management a little bit more complicated and see how that feels. Too much code to read, but what did I do? What did I do? I now have scream many. Stop trying to define it, please. Thank you, Apple. And it can take 3 command line arguments. OK, so it's the same thing, but now we can handle more than 1 command line argument. Fair enough? So we're going to zoom in. Here's the main code. And I've got some helper function, and we're going to look at that in just a second. But it's returning a list of screaming outputs to me. OK. And I loop over the list, and I write to each of them. And I loop over the list, and I clean them up. And it's kind of annoying that the cleanup is 3 lines. And final piece of Python trivia, the with keyword doesn't work very well with lists, unfortunately. This is a common symptom of languages that have similar features. Try with resources in Java, using in C#. I don't think any of them actually work directly with a list. It's a little bit unfortunate. But my bigger concern is what this function open outputs looks like. Because the happy path through this, we know what this function's doing, right? It's opening all the arguments that we passed in. The happy path is 4 lines of code. Couldn't be simpler, right? Create a list, loop over the paths we got, open each one, stick them in the list, return the list, right? This function is dirt simple. But the error handling code is longer than the happy path. And of course, we can't use try finally here because we don't want to close these files if we successfully open them all. We want to hand them back to the caller, right? So there's like some ownership stuff happening here. And this is not that unusual. We write functions like this all the time. We need to remember to use except instead of finally. We need to remember to re-raise the exception here. With does not work well here because it behaves like try finally, right? We don't want the with keyword to clean up in the success case. Golang's defer style cleanup also gives us problems here, right? Even if we could write the cleanup we want to run, we don't want it to run at the end of this function if the function succeeded. So I put this on the screen and I'm complaining about it. I mean, this is not like the end of the world, right? Like this is, if you've written Python or whatever language for a few years, none of this is unfamiliar. You can do this. But if we got a couple dozen functions like this in our application, we're probably not going to get this right every time. Like what are the odds that you wrote a test that makes sure that you re-raise the exception if you fail to open a file? We don't write those tests, right? It's a little bit annoying. And so with that in mind, what does Rust do? Here's the Rust code. Same idea, right? We've got multiple command line arguments now. We're going to open them all in a loop. And I just want to look at that helper function. Here's open outputs. Where's the cleanup code? There's no cleanup code. This is the naive, simple way to write this function, to the extent that anything can be simple in Rust. This is the straightforward way to write this function. This is the way I wrote it the first time. This cleans up the files correctly in the happy path and in the error case, which is to say it doesn't clean them up in the happy path, right? So if we return outputs to the caller, this is what Rust calls a move. A lot of us know the magic buzzword move semantics. This is a move. We're returning the outputs vector by value. And so it is not going to be dropped at the end of this function if we get to that line and return it. But if we don't get to that line, because of the syntactic sugar magic of the question mark operator, we might encounter an error. We might fail to open a file. We might return early. And if we return early, then the local variable outputs gets cleaned up at the close curly brace. Wow. This is remarkably convenient. If you care about freeing resources all the time, this is very exciting. Not everybody is as excited about closing files as I am. I can admit that and understand that about the world that I live in. But I think the most exciting example of this property, this sort of move semantics, destructor-based cleanup, this like nice automatic stuff, is how it looks when we do this with locks and mutex and multi-threading. And I'm going to throw an example on the screen to torture everyone. Bear with me. Let's first look at a simple function that is not doing anything to do with locks or threading, because I want to get the structure in our heads. This function is called add one to smallest. It's not even a program. It's just a function. It does what it sounds like it does. We've probably all written this loop in some language, right? We start at index 0. We loop over all the other indexes. We have a list of ints. That's the argument, right? This list of 32-bit integers has been given to us. If you haven't seen slices, don't worry about it. It's a list. We loop over all the other indexes in the list, and we compare each next integer that we see to the smallest one we've seen so far. If we see one that's now the new minimum, we update. And then at the end, smallest index is referring to the minimum entry in that list, and we do something to it. In this case, I add 1 to it because that's what I said I would do. Good so far. No, nothing up my sleeve, right? OK. Here's the multi-threaded version. It's the same code, same algorithm. And to be fair, there are no threads on the slide here. I'm not spawning any, but I'm dealing with locked data that could be accessed from other threads, right? So instead of a list of ints, I have a list of mutexes. So in Rust, the mutex contains the data that it locks. So each of these integers is inside of a mutex, and we have a list of such mutexes. That's what we've got. The structure of the code is, of course, the same. We start at index 0. We're going to loop over all the indexes. We're going to do some sort of comparison. And then at the end, we've got the minimum, and we do our thing. So we already know what this code is doing. How does it do it? We have the lock method. I'm going to ignore the unwrap entirely. It's not that interesting. It's something error handling. But lock returns a mutex guard. OK? So once again, the C++ programmers in the audience know what's going on, because at least one, the mutex guard has 2 jobs, and one of them is exactly the same as in C++. Its job is to unlock the lock, right? So when the mutex guard goes out of scope at the closed curly brace or whatever, when it's cleaned up and dropped, it unlocks the mutex that it came from. This is nice because we can't forget to do that, right? That cleanup is automatic. That cleanup is correct in the error cases. Super convenient. C++ does this too. So that's the first job of mutex guard. But in Rust, there's a second job. And we see what's happening here. So when we refer to those integers, we do the little star thing with the guard. So if you are coming from C or C++ or Go, you know and love this little star, or maybe you know it. And you know what's going on here, right? This is the pointer value distinction. We are dereferencing a pointer in some sense. The mutex guard is like a reference to the value on the inside. If you have not played with one of those languages and you've never seen a star, please squint at it until it goes away. Right? The mutex guard is sort of behaving like a reference to the integers that it protects. So we get to write the same code that we were writing before, and it still works. I'm not going to claim that it worked the first time I wrote it, but it works now. Cool. OK. Why am I torturing us with all this? Because I want to think about where the destructors run. Where does the cleanup happen? Like, where actually do we unlock the locks in this code? There's 2 places, sort of, 3. One thing is easy to spot, right? OK, so smallest guard is a local variable. It goes out of scope here. OK, so half the story is that at the end of the function, whatever smallest guard is holding goes out of scope, gets cleaned up, and unlocks its mutex. That's half the story. The other half of the story is next guard. Now, by default, next guard would go out of scope here at this closed curly, right, at the end of the loop body. So by default, every time through the loop, we should unlock whatever next guard was locking. However, this line is very interesting, because what does this line do? This line moves next guard into smallest guard. So that same move semantics we just saw on the previous example with the outputs is showing up here. When we move next guard into smallest guard, that means 2 things. 1, next guard is not going to get cleaned up when would normally go out of scope at the close curly, right? It's been moved away. It's not going to get cleaned up here. And smallest guard needs to get cleaned up and dropped before we can overwrite it. This is, again, I'm going too fast to get into the nitty-gritty details of move semantics in Rust, but this is how everything works automatically under the covers. And what that means is that every time through this loop, we unlock one mutex guard, but which one we unlock depends on which code path we take. And if this condition is true, we unlock smallest guard instead of next guard. And I feel two different ways about this at the same time. Like, on the one hand, I think this is like amazing. It is incredible that this code is nice and tight and compact and clever like this. The the with keyword, if we were using with to manage locks, would absolutely not work here because the lifetime of next guard is not constrained to a specific lexical scope. It is phenomenal that we can do this. It's also terrifying, right? Like, anyone who's played with multi-threaded code knows that you're going to make a mistake and you're going to like lock the same thing twice or whatever, and you're going to deadlock. We probably want to be thinking very carefully about exactly how everything gets unlocked. And shouldn't we be a little worried that Rust is trying to be so clever here? And the best thing about all of this is that Rust's answer is, don't worry about it. Because when we make mistakes, almost all those mistakes in code like this, they're compiler errors, right? I just like fell asleep, right? And I swapped two variables. And now the code doesn't make any sense anymore. It's certainly not like finding the minimum. It's like doing some nonsense. More importantly, Rust agrees that this code doesn't make sense anymore. The important thing is that we're now moving out of smallest guard instead of into smallest guard. And you can't do that more than once. It's the short version of why Rust doesn't like this code. It's just a compiler error. And I'm not saying it's easy to understand the compiler error. That is a learning tax that we pay. But the compiler will tell you when you screw this up. One more example of this. This is a little bit syntactically heavy. If you have not seen this like funny combination of sigils in Rust, I apologize, and we can squint at this one too. This is me trying to take a reference directly to the integer on the inside of the mutex, and I'm holding onto that reference instead of holding onto the mutex guard that it came from. So maybe the clearest part of this is that I've changed this type. Right? This is valid syntax. You can do this in Rust, but I've screwed it up because what have I done? I have made it so that now when several things are screwed up, but one of them is when I move next into smallest, I'm only moving this. I'm not moving this. And so now, in that case, this reference that I've held onto is trying to outlive the mutex guard that it came from. And that's all very confusing, and it takes a lot of getting used to before you can understand what the compiler is telling you about examples like this. But the important thing is the compiler catches the mistake. And this sort of thing is impenetrable as it is. This is the reason why we can't have this nice thing in Python. Right? I mean, like, this is the reason why we don't want our managed languages doing this kind of like aggressive implicit cleanup. Because it is so easy to hold a reference to something. Maybe I stuck it in a list. Maybe it's in the field of some other object. And that variable went out of scope. And now it's been cleaned up, but I still have a reference to it, that the bugs that result from that, like if there wasn't a compiler catching our mistakes here, this would actually be quite painful. Right? And so, of course, the garbage collected languages do the garbage collection thing, right? They say, OK, I will figure out whether you're still using this value. That's the promise of garbage collection. That's what makes it so nice. I will figure out whether you're using the thing, and I won't clean it up until then. And that's great. It's especially great with memory. But it's not so great with resources because the cleanup doesn't come soon enough. So there's this unfortunate trade-off, where in the garbage collected languages, our beloved sort of convenient mechanism is no longer appropriate for the problem, and we have to do everything by hand. And trying to introduce features like this into Python would not go as well as it might seem at first glance. So, final section. Any questions? I realize I'm just like blazing through slides. Aliasing rules. So, who's written this bug before? I know I'm throwing a lot of code on the screen. What have I done? There's a person, people have favorite foods, OK? And everyone likes donuts. So we're going to start with a list of donuts. And then, of course, Alice likes donuts, and Alice also likes apples. So we're adding that to her list. Bob likes donuts, and Bob also likes bananas. So we're adding that to his list. And then we're printing everyone's favorite foods. And we know exactly what we expect to see. But what we actually see is that everyone likes apples and bananas. Why? It's a reference, right? Aliasing, spooky action at a distance. This is why, right? The reason why is because we gave a reference to the donuts list to each person. Everything in Python is passed by reference. And so when they modify, or we modify their lists, we're actually modifying the one list. There's only one list, and we just have two references to it, right? And we have done something confusing, and we find out about it at runtime. How do we fix this? again, I think everybody has used a language that is vulnerable to this problem, and everybody knows how to fix it. We copy the list. And there are different ways to copy the list in Python. I do it this way. Some people use the square brackets with the colon in it. And that's fine. And that works, and it fixes the code, and we can see that the output's correct on the right. Subtle point here. I do like to point out, this only works because we have like one layer, like we have a list of strings, and the strings are immutable. But if we had like a list of lists or a list of dictionaries or whatever, like we only copied the top layer. And so we can still have this bug even though we tried to fix it. We need what's called a deep copy, and different languages do that in different ways, and it's kind of annoying. Fine, that was a subtle point. This is a simple case. The fix works fine. I'm going to skip through the Rust code and just look at the Rust fix. The Rust fix is the same. So it's called clone instead of being called list. We've copied the list, and now each person has their own copy of it. The second clone was probably optional. We could have, used donuts in the second place. The same thing was true of Python. But OK, so it's the same fix. But the interesting thing is that the mistake, I went back, I don't have the fix, the mistake doesn't compile. Right? So when we make this mistake in Rust, the compiler catches it for us. It's quite nice. What's happening here? This is that same move semantics concept, right? Assigning donuts to favorite foods is moving donuts. You can't move it twice. There are other ways to make this mistake in Rust. This is another bit of review for the experienced people. But this is a very interesting story for those of us who have not yet played with references. We could try to write the code this way. The folks who know what that star was before know what the ampersand is as well. This is a reference. This code is trying to do exactly the same thing that Python was doing, really. Right? This code is trying to have two different objects with references to the same list. And you can do that. These are what we call shared references. You can construct that. It is legal to construct these people, but of course it is illegal to do the following line. Right? Shared references in Rust are what C and C++ call const pointers, const references. Right? You typically cannot use them to do mutation. So the compiler catches the bug for this reason. We violated this rule. We tried to do mutation through a shared reference. Of course, there are also non-const pointers, right? Sometimes we do want to do mutation through a reference. We call those mutable references, and that also doesn't compile. If we try to make the mistake with mutable references, we've run into a different rule. It's kind of like the move semantics rule, like you can't move something more than once. It's sort of like that, but the rule is you can't have more than one mutable reference to the same value at the same time. Mutable references are temporary. They don't move the value, but they need to be unique while they exist. They cannot overlap any other mutable reference. They cannot overlap any other shared reference either. It's a very strict rule in Rust. This is probably the biggest learning tax you pay when you learn Rust. And the reason we are sometimes happy to pay it is because it catches bugs. A couple other versions of this bug as I blaze through my time on the way to 45 minutes. I've added add favorites to person. Right, so you can take someone else's favorite foods and add them to your list. Question? Yeah. No. Well, yeah, so the question is, what if we want the donuts to be shared across two instances? And if I can choose to interpret your question in the friendliest possible way, the answer is this works fine as long as you don't need to change them. You can totally do this. And there's some lifetime issues, and we might introduce something called an arc, and we don't have to worry about it. Right. So if you have a thing that is both shared and mutable, then you have opened up a very interesting and rich conversation topic in Rust. There are a lot of options. We saw mutex a couple slides ago. So one way that you can do this is you can have a mutex, or there's something called a ref cell that's like a single-threaded mutex. It's kind of obscure, but mutex is very common. We use this all the time. You can have a mutex lock something, and then you can access it from multiple threads. Now, if you're doing it from one thread, it feels weird to use a mutex. And so usually what we say to do is to restructure your data so you don't need the references. It's very common for people to use indexes instead of references. There are various strategies. After I log off here, let's look at some examples together, because there's a lot to talk about. Yeah, how do you actually mutate shared objects without a lock is a very interesting set of questions. Yeah, totally different talk. Right, so we just saw this. So of course the problem here is that Alice is adding favorites to Alice. And what does that do? The answer is, like, we don't want to know what that does. It turns out that what it does is like loop forever and allocate all the memory on my machine, and then like my desktop stops, like the mouse doesn't move, and then eventually like Linux kills it. Like that's what it does. Right. And that's trivia, right? Like we shouldn't want to know exactly what happens if we modify the length of a list while we iterate over it, because we should just never do this, right? This is a mistake. It's not a good idea to write this code. In some languages, we call this category of mistakes iterator invalidation, something like this, right? In C++, it's a famous source of memory corruption issues, even in modern C++. It's very easy to invalidate an iterator into your vector, things like this. In Rust, this doesn't compile. And it doesn't compile for the same reason we saw before, right? It's that mutable aliasing rule. So here we see a shared reference to Alice. What we don't see is that the dot implicitly creates a mutable reference to self, which is also pointing to Alice, but the compiler sees it. This code is illegal. So you just can't make this mistake in Rust. You really just can't invalidate an iterator. One last flavor of the same bug. I think most of us have probably done this too, right? We have a list of functions. We add to that list in a loop, and I kind of expected this code to print 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but it doesn't, does it? It prints a bunch of 9s. And then we all see this and we're like, oh God, that thing again, right? This happens a lot. Golang, those of you who know Golang already know that Golang 1.22 earlier this year changed the spec semantics of for loops 14 years after the original 1.0 release of the language to fix this bug, because this bug is so common, right? Yeah, I don't know what their backwards compatibility story is for that. I'm sure they looked at it. I think their conclusion, the Golang people, the question was, what happens if you're relying on that behavior? I think the conclusion was no one ever knowingly relied on that behavior, which might very well be true. But it is interesting that these things that we would never want to do are so easily doable. In Rust, this doesn't compile, right? It doesn't compile. In this case, it's a lifetime error, but you could just as easily think of it as a mutable aliasing error. If we want to fix this code in Rust, we have to use the move keyword. And probably half the room has seen that. And for the other half, it's kind of a weird name. And this is another learning tax that we pay. That is the magic keyword that fixes the problem. The important thing about this example is not that it's obvious how to fix it. I think it's quite non-obvious. But the mistake doesn't compile. And that's the consistent story. It's very nice. Once again, the best example of all of this is multi-threading. So it's maybe not everybody's as excited as I am about writing lambdas in a for loop correctly. I don't know. Maybe we like debugging that. But getting our multi-threaded code correct is very exciting, and there are very few languages that can help us with this. So here's a quick example of just adding up a bunch of integers. This is single-threaded code. I've used a fancy for each iterator method instead of a regular for loop, but we can see what it's doing, right? It's adding all these values to sum, and it's asserting their value at the end. I've done it this way because this makes it very easy to multi-thread the code. So I can import a library called Rayon, and if I do that, and I toss on this into parallel iterator helper method thing, it will do some magic such that the for each method now runs that little body, that closure, from many threads, and it spreads the work out. And this is a stupid example because it's not a lot of work, but in theory, this is very convenient and fun. The problem is it's broken. This is a race condition. This is a data race. This is going to give me the wrong answer. It's the ATM problem, right? 2 ATMs. I read my bank balance. I add 100 to the number that I read. I write my bank balance. They're stomping on each other's work, right? This is a familiar bug if anyone's played with multi-threading. I've written that bug. And in fact, in the memory model, it's not even just the wrong answer. It's actually undefined behavior to write this in Rust and C and C++. And Rust will not compile it. Rust can see the difference. We don't have time to talk about the technical nitty-gritty of exactly how Rust sees it. There are traits to do with our lambdas and closures that take a little bit of getting used to. And we can look at that after this talk if you like. It's quite fun to talk about and play with examples. But the important thing is that Rust can see that, oh, this thing's going to get run on multiple threads. That means that we have a shared reference to the closure itself. So it had better not be using mutable references to the outside in its body. That is effectively what Rust sees here. And this is too much detail if you haven't yet played with mutex, but we saw mutex before. And if you toss the mutexes in the right place, you can still use all those threads, and it compiles just fine, and you get the right answer. So I am very confident that the compiler deletes the entire loop in the single-threaded case and puts a constant in there. And in this case, it doesn't. So this is probably infinity times slower than this. Its speed relationship to the code that cannot run is another fun joke of a question. So this takes getting used to, and I'm not saying that you can easily use mutex the first time you sit down and do it. But what you can rely on is that the compiler will tell you when you didn't do it right. And that's a big, big difference. We were going to have a talk about functional programming languages. And I look forward to the day when we can have that talk. These languages, a lot of us learned something like this in school. I learned Scheme, that's the one on the right. Some people use Haskell because they're cooler than me. And these languages had a reputation for a long time of catching this entire set of bugs. And I think that reputation was well earned, right? These languages are famous for not allowing the kind of spooky action at a distance bugs that we were just talking about. But they use a big hammer to get that guarantee, right? They either don't allow mutation at all or like highly discourage it and it's confusing. But like they don't do mutation approximately, right? And it's a big benefit, right? Catching all these bugs is a big benefit, but that's a big price to pay. It's a learning tax, and in many cases, it's a performance tax. And Rust has come along and kind of given us a third way out of this problem. It's like it's not the big hammer. It's like you could think of it as a smaller hammer, or just like not a hammer at all. Like you can do mutation, you can do aliasing, you just can't do them at the same time. That's the rule in Rust. Subtle, and it takes getting used to, and it's a big learning curve. But once you've got it, you can write the programs you're used to writing. You can do the normal, like we're going to all mutate the same value and we're having fun. And you can write that code. You just have to write it correctly. It catches all the same bugs without the big trade-off. So I think this is the other half of why Rust is as hyped as it is, right? Yes, competing with C++, that alone is probably most of the story. But this other half, where sometimes it makes sense to consider Rust, even for the stuff we could have written in Python, I think that's pretty hype. Anyway, I've been lecturing at you guys for way too long. I had some bonus slides about cargo script. That's kind of fun too. If you want to talk about it, find me afterwards. Thanks very much. Question?
To make a comment.
Comment, not a question.
You hear people say in that the nice thing is if it compiles, it works. That's true, and a lot of your things, I'll end up there and just be like a monkey writing Shakespeare, adding asterisks and or ampersands until it compiles. And I'm like, well, it's not too complicated. But if the compiler takes it now, it probably really does do what I intended originally, and yes, the compiler says it's okay.
If it compiles, it works. It's right. People said that about Haskell for a long time, and I think that's very true. And they say it about Rust. I once saw a Hacker News comment that used that same phrase, if it compiles, it works, but they were talking about Go. And so I decided to never use that phrase again. That's rude, and I apologize for telling that story. Oh, do I have a thing?
Oh no,
well,
I'll
I
fix
can
that.
at least
Thank you.
Close it.
Thank you.
There, problem solved. Thanks.
Oh, keep going, keep going.
Well, any other questions, I guess, while we transition? Or are we, is this the last thing?
It is not the
It's
last.
not the last thing. Okay, well, we'll not take an excessive amount of time, but there's a question.
Complicated problem of lifetime, because in general, once we pass something into a parallel in a regular Rust, can't tell what we're done with it.
Right, the question, yeah.
Other tasks.
The question that was also a comment is that there are a lot of details around lifetimes. It's like trying to share objects and then not running afoul of the borrow checker and actually getting your code to compile. In the early days of Rust, well, yeah, I guess, so the solution that was always around is you put things in an arc, and that's another type that you have to learn, and it sounds like you're already familiar with that. That Rayon library that we were just looking at, we saw an example where it's borrowing the local scope, right? Sum is a local variable. And this has no problem sending references to that local variable off to other threads. So there are contexts where we can do this sort of scope-based threading that almost like magically work and just don't have any borrow checker problems at all. This is not a standard Rust API. There is a scoped threading API in Rust that is standard. It works a little bit differently from this, but that was not around for many of the early years. So the story there has evolved over time. There's a lot to talk about, just like shared object mutation. Big story is a lot to talk about. Yeah, lifetimes in particular. It's one of those things that we should probably have somebody get up here and teach us all. Yeah, what's it all about? All right. Oh, yes, one more.
I didn't know much about it, so I don't know if I can like kind of figure out what happened, but I'd be curious like how it actually happened.
Yeah.
But I was working like cryptocurrency, maybe that was the first problem. There's that point they're like, oh yeah, we're gonna write it all in Rust and stuff. And I think they were using Tokyo, and I think maybe maybe a bug in Tokyo or something, but I kind of did something nasty with LSO count file handle the process basically so it doesn't and restarted so it doesn't take, but I guess it's
Nuke the world. It's always a
maybe
good fix. Yeah.
yeah. Bug in like but I guess
Yeah, I
I'm
think
not sure
it.
where I was going with that. I thought it was
It's I think it's important to clarify. Rust provides a lot of great resources, right? Like Jack just showed us to clean up our file handles, etc. But it's important to clarify that in Rust, a data leak or a leak is not classified as a safety issue. So in other words, Rust does not provide you a guarantee against leaks. It does not provide you a guarantee against deadlocks. It does not provide you a guarantee against race conditions. A lot of people confuse race conditions with data races. They're not the same. So
The whole talk, right? Yeah.
yeah, there's a whole talk right there. But there are a lot of things that Rust helps you with, but doesn't provide the ironclad guarantee, right? What we call fearless concurrency, fearless memory safety. Rust is not fearless with regard to leaks. So how can you leak a file handle? You can leak a file handle by putting it into a graph or a data structure that's self-referential. Okay, so if you have something that says on the last, many people can point to me, and then as soon as I'm done, as soon as nobody else is pointing to me, I will drop and I will clean up myself. So if you have the file handle in a node that's pointing to a node that's pointing back to it, whether it's directly or through a whole chain of other nodes, if there's a circular reference in there, none of the nodes involved in the circular reference will ever drop. The compiler won't tell you about it, and you will leak. So it's possible you had a situation like that.
Stick it in the box and leak it too.
Yeah, there's actually a very good, there's an API called box leak for exactly that reason. Sometimes you want to leak something for a very good reason. So there's an API to actually do that on purpose.
Yeah, I think one of the most interesting things to do with a program like that that's leaking files would be to run it through Valgrind and see if it's leaking memory. Because if it's one of these situations where we've created a reference cycle, as we can do in Python, but Python has a cycle collector, Rust doesn't, C++ doesn't. If we do this, then we're like leaking these objects and whatever they contain. So that's one way to do it. My first guess would probably be that someone has a custom file type and they wrote the destructor wrong. Like I could go looking for like how that file was created, but yeah. There's a few different options for that story. Usually it's kind of hard to create these cycles, especially as a beginner. You have to jump through a fair number of hoops to even create a reference cycle in Rust, but it is possible. That's a different talk.
Thank you, Jack. That was great. My mic is back on. I can hear it. All right, so we've got about 30 minutes. And who here would need a break? I got one. I got two. All right. So if you need a break, go. But in the interest of time, I'm going to keep moving because I'm actually going to go back to what we said we wanted to do for beginners talks. There's a talk that I thought might be pretty appropriate. And instead of waiting for August, I'm going to give you guys maybe a bit of a cliffhanger tonight. So I'll start the August talk tonight, and we should have enough time to at least get to the cliffhanger. And what's amazing, we didn't plan this, but what's amazing is this is very, very apropos to the talk we just had. So this will follow on and help reinforce some of the concepts that Jack just showed us. So you ready? We good? All right, let's do it. All right. do I have? So what I'm going to do is I want to talk about a topic that might not sound like a beginner topic at the beginning, locks. But the thing about locks is that they're very important. If I can find there we go. This is the picture that I wanted to show you guys that was at Mozilla. Must be this tall to write multi-threaded code. What is going on here, right? Writing multi-threaded code, as we just heard, is a bear. What we would like to have, fearless concurrency. I think we got pretty close. So let's talk about how all of those concepts fit together. So because this is going to be a beginner talk, I'm going to start right from 0. I'm going to use cargo new, and I'm going to call my app locks. And I cd locks. And I'm going to use Rust Rover as my editor. And what you're going to see is a main. And I can run this code, and it will say hello world. This is cargo, plain vanilla Rust. Once you install Rust, you can do cargo new, and then you can type cargo run, and this is what you'll get. So the first thing I want to do is write a little program that counts to 100,000. So I'm going to do that in a very modular style. So you're going to see a way of putting this together that is probably more complex than what you might do for a beginner, but it gives you some exposure to sort of how you might want to think about writing industrial strength applications. So I'm going to have a module called, actually, I think what I'll just do is say, yeah, I'll just say mod. I'm just going to have a module called counter. And all a module is just a file. And this file is going to contain one thing. It's going to contain a publicly accessible global variable that's mutable. So any of you who are interested, or any of you who are familiar with Rust, or just heard what Jack just said, knows that Rust does not like that, right? You heard alias or mutable. Let's do both. So static mute, and we're going to call this counter. It's all caps just due to a convention. There's nothing Rust specific about that. And we're going to just use an unsigned 64-bit value, and we're going to start it out at 0. Okay. So all I've done is I created a variable that sits in a place in memory that can be accessed by anyone, anywhere, anytime in this process, in this program. And it's mutable. So when I compile my program, we're all still good. It warns me that nobody used that variable, but that's okay. We'll fix that. Times, and then I'll say, so now what I'm going to do is I'm going to say hello world times however many the counter got up to. But because counter is defined, all caps, is defined in a module, I'm going to say use counter. And my IDE doesn't know that I'm using it, but it's getting used. And so great, it's going to work, right? Here's our first problem. Any beginners want to tell me what they think or know is the problem? Right there, yes. Yes. So I've created the ability for anybody to change this variable. And it says, well, you can make one. That's okay. But as soon as you try to touch it, I'm not going to let you. Right? Remember the rule. Aliased or mutable, not both. So I can create it, but as soon as I try to write it or read it, it's possible that somebody else might be doing the other thing. We know that there's no other tasks running, but the compiler can't verify that. So the static guarantee, it says, nope, as soon as you tried to read that, no go, no go. No problem. We're going up to the next level. Easy, right? Just tell it, trust me. I know what I'm doing. Okay? We had some people wanting to learn about unsafe today. This is what not to do. Okay? So here we go. We're going to, I think I might need a semicolon. It's like, yeah, it works great. It's at set to 0, right? And now I'm like, we're going great. This is fantastic. So what I'm going to do here is I'm going to make a loop running from 0 to 100,000. And I'm going to iterate each time. I don't need the index from this loop, so I'm going to prefix the index with an underscore, which means I'm not going to use it. And I'm going to take counter, and I'm going to increment it by 100,000 times. And it's going to tell me, you can see the red squiggle under counter. It's going to say, hey, you just used a static mute. Now I'm writing to it. It's like, no, can't do it. So it's like, no problem, we know what to do. We got a solution for that. We'll just throw that in our unsafe block. Yes. Okay. By the way, this is C. This is C++. This is where we're living right now. This is 100%. You don't need to write the word unsafe, and then off you go. And I'm not being mean when I say that. This is just exactly how the languages are built. Off you go. And it works. What's the problem? Crazy Rust people. What's the problem? This is great. Okay. So now you're like, okay, I now know how I'm going to write all my Rust programs. Right? Main, unsafe, go. Right? You're off to the races. No more fuss. Right? You guys wanted to know how to write Rust programs with less hassle. Well, here you go. So here's what we're going to do next. My CPU is getting worked over, incrementing it 100,000 times. I've got 10 CPUs in here. I got 12, I think, or 16. I don't remember. I got a lot. But let's have 10 different CPUs work on the problem so we can get it done faster. So I said, okay, sure. So I'm going to go 0 to 10. And what I'm going to do is I'm going to do another for each. And in here, I also don't care about my task. Just say the number that I'm doing. I don't care about that. And what I want to do now is every time my 0 to 10 loop runs, I'm going to spawn a thread that's going to increment counter 100,000 times. Did I do 10? No, I did 100,000. Okay. So when we're all done, I'll have 10, presumably 10 cores running on this counter. Now we're exercising that globalness, right? And we're going to get to 1,000,000 in the same speed that we got to 100,000. It's going to be glorious. So first thing I need to do is I need to tell Rust that I need to spawn this 10 times. So there's an API call that's in the standard library called thread, and it says spawn. And now you're going to get into some weird Rustisms that can be very difficult to read. What's this? I'll just read one of these for you to help you sort of understand how you break these down. This says that the spawn function takes a parameter called f. We're just going to call it f, where f implements some trait as effectively a function pointer. The function pointer has nothing in the brackets, so therefore it doesn't take any parameters, and the function outputs some type called t. So you're like, what the heck? You're taking a parameter that's a function. Wait a minute. This is a higher level function. This is a closure. So what you can do is you can call spawn and you can hand it a function, and it will run that function as another task. So that's what I'm going to do. Now it's going to give me back something called a join handle. We'll get to that in just a moment. But now that I understand a little bit about what's going on, I'm going to tell spawn So for a closure, by the way, is another way of main here is a function definition, but it has a name. It's called main. If I wanted to make another function that doesn't have a name, I'm going to use a closure, and the variables or the bindings that I'm going to create go in these vertical bars, but there aren't any parameters coming in. So I'm going to create a function, and that function is literally going to be the thing we just did. We are going to spawn 1 or 10 functions that are 10 closures that are going to actually count to 100,000 each. All are going to manipulate the very same global mutable counter, which we know works because we just saw it. I've got one thing now I have to take care of is this thing called a join handle. Spawn returns a join handle. So the error message is a little bit cryptic here, but what I'm going to do is when I spawn a thread, I spawn the thread, but the OS is going to give me control or give me a handle back to that thread, just like we did with the file descriptors. So I can, hey, is that thread done running yet? Did it crash? Did it panic? I can maybe, I can query that. So I'm going to go ahead here and say let threads, it's going to be a vec. So I'm going to have a vector, which is growable. And then I'm going to make it mutable because I'm going to add to it inside this loop of 10 because I'm going to make 10 threads. So I'm going to hold 10 handles to those threads. So here's where I'm going to say let thread equal. And you can see that I'm getting a join handle back from spawn. That's the thing I need in order to be able to talk to the thread. And then I'm going to add this thread to my collection of threads. So threads dot push thread. And now that completes my for each. All right. So what the heck is all of that? To summarize, what I've just done is I've created a bucket to hold a reference to all the threads I'm going to make. Bucket's empty on line 7. On line 8, I'm making Rust agreeable. On line 10 or 9, sorry, I said I'm going to create 10 threads. And now I'm going to go ahead and actually spawn those threads. The OS is going to create new threads, and they're all going to run. It's probably going to assign them to other cores. And each of those threads will do this. They will take in no parameters because there's nothing to do, and they're just going to run. As soon as they're done, they're going to drop off the end. There's nothing to do. There's nothing to go back to. They're not a function call. They're actually a thread. So the threads will be done. My handles in the main thread will be able to query that and say, oh, when you're done, let me know. So that's what I'll do right now. I'm going to say, hey, let me check through all of my threads. Actually, I'll just do, what is it, threads dot iter. So I'm going to turn my vector of threads into an iterator. I'm going to look through every one of these. What's in here is actually my join handles. So you can see that it's telling me my join handles are in here. And what I'm going to do is I'm going to visit each one and I'm going to park. I'm going to block. I'm going to wait until that thread is done counting to 100,000. And when that guy's done, I'm going to move to the next thread handle. I'm going to wait until that guy says it's done. Clearly, by the time I get done the first one, the other 9 will be done. So that block won't even block. I'll just be able to rip right through them because they'll all be done. But what this does is it assures us if we have a lag, somebody's lagging, or I have an efficiency core and not a performance core, and it's not done yet, it doesn't matter. We will wait sequentially to make sure that everybody's done before we give the grand total of our million here. So let's go to handle, and I'm going to say handle.join. And what that's going to do is it's going to say, hey, I'm going to get a result. That result is going to basically tell me whether or not the thread is done. But if my thread panicked, say it was doing some math, arithmetic, or something and panic, I'm going to get a different response from my join handle. So I actually have to handle the error condition. So there's another way to iterate where you can deal with fallibility. So I'll do that. And then I'm going to, because I hate unwrap with a passion, unless it's in my tests. So that's fine. All right. So what am I going to do? I am going to return, or I'm going to, if I get an error because one of my threads panic, I'm going to exit my entire program, but I'm going to print out an error code. The error handling talk that we'll give will explain this a little bit, but I'm going to write a line of code here that is probably going to make you guys be like, what the heck? But it does make things work given what we're going to get back from join handle. It actually has a lot of the things we talked about today. So I'm going to redefine result. I guess I'll do this. All right. Dine. There's dine, there's result, there's what the heck is any, bunch of crap. Okay, so we're going to look at this, now line 7 and say pretend result is okay, gives you what's called unit or nothing. Some people might know this as void. And error gives anything my code wants. Okay, so any type. I'm getting rid of, we're now dynamically typed. The reason for that is if we look very closely at what join handle returns, the error case, it's actually an any, because it's giving us information about what my thread was doing. There's no way the standard library can know, say, what my thread was doing. So they're being very general about what information they're giving me back. So that's an unfortunate part about this demo for beginners. But this is a line that just, we can ignore it and just understand that the concept is I want to be able to return an error here rather than throwing unwrap, which is panicking. And if we're not clear as to why we do or don't want to panic and what's the difference between a panic and an error, I think that would be, a great topic for another time. Just say that for production code, for quality code, for reliability, you prefer errors over panicking. In general, there are exceptions. I shouldn't use that word either. Yeah, that was not intentional. Anyway, so there we go. So we're going to do the join handle, which is going to give us back actually, I don't think I need to do anything now. I can. All right. So now threads, going to iterate over all the threads. We're going to try, in other words, it's possibly fallible. For every item in threads, which turns out to be a handle, we're going to try to join each handle. As long as the thread doesn't panic, we're going to get a result out of this, which is what try is looking for. And try, as long as we keep getting okay, try will keep iterating through the list. If one of the join handles returns an error, try for each will stop iterating and will return an error, which we're going to handle right here with this try operator. We're just going to exit our code, returning the error to the user. Okay, that's what's going on here. And now it's telling me that at the end of my main, I'm not returning a unit type like I promised in my type signature. Okay. So here we have beaten Rust into submission. Does it work? Does it blend? Oh, my fancy Dine. Thank you. Yeah, I forgot box. There we go. Yeah, I need to ref that if I wasn't gonna box it. Wait. It could be hexadecimal. So wait a minute. That's not a million. Rust can't count. Okay. Let me try again. Try again. I'm sure it's okay. Oh. Huh. Wait a minute. That's 107. That's 117,000. 90% of the writes we just did were lost. This is 90% data loss, this code.
Must be that Apple chip.
Exactly. Must be the M3, right? It's got to be. It's got to be. Oh. No, and I wasn't joking, right? We could write this in C, the exact analysis code, and you get the exact same result. What is going on?
Sign release mode.
That's it. That's it. You're brilliant. I didn't figure that out. Okay, so whenever beginners are running Rust code, the number one, it's like, oh, why is Rust so slow, man? Basic is faster. It's always, did you run it in release mode? They're like, oh, right? They didn't know. So just dash release. That's all you need. And then your code goes faster. Code goes zoom. It works. It works. You fixed it. What? It's not awkward at all. I know exactly what it's doing. What is going on? Oh, that's a million. It got it. It's perfect.
Run again.
All you need is release mode. That's all you need. It's gonna work. Optimizer says, oh, I know what he means. It's a constant. It's really fast. We could, I mean, how much time do we have left? Because we got 6 minutes. We got time. We'll take this over to Godbolt, and we'll see what it's doing. We'll see what it's doing. Okay. Oh yeah, we can ask that too. We got 6 minutes, right? All right. So we got to be good. Once we're done, we got to hustle out of here because we don't want to keep our hosts late. But this is really interesting. What is going on? Our code is losing data left and right. Okay. This is a data race. This is not okay. This is the cliffhanger I'm going to leave you with. I'm not going to give you the answer until August. But I have to let you know, because there's like basically 3 parts I want to do to this talk. So this is part 1. We had the time, so we can do this. Part 2 will be using locks to fix this. And then part 3 is, wow, locks were kind of tough. Is there a better way? And we'll walk through all 3 ways. Or all 3 parts. So one question for you real quick. I personally will be in Toronto on August 15th when our next meetings is scheduled to be held. So I've asked, they think we can move the meeting back a week, and we can do have the meeting a week early next month. Would that work for most of you? Yeah. Okay, cool. All right, then I'll proceed with that. I will update the date on this slide, and I'll inform everybody on Discord when that's been approved by Microsoft. We'll go from there. And what I'll do, I think in the interest of courtesy for them, we got 4 minutes left. We'll save our Miri exploration and our Godbolt exploration for August.
We're gonna do it.
Or we could do it at the bar. Right. All the people who weren't at the bar would be like, what happened? How did you guys get so advanced? All right. All right. So yeah, important stuff. All right.